All right, well, in the last couple of class periods, we went over trig function stuff. And we looked at it as it applies to the unit circle, and then as it applied to right triangles, okay? Now what we're gonna do is we're gonna get into chapter 6, and basically, okay. We're gonna look at the graphs of trig functions. So the graphs of various trig functions. Now, I put 6.1 and 6.2 on there because the sine and cosine are 6.1 and the other trig functions are 6.2, but we're kind of going to talk a lot about graphs of trig functions in general. Okay, so we're going to look at the graphs of trig functions. So our base trig functions let's look at y equals sine of x and, or not y equals, I'm sorry. We want to use function notation. So f of x equals sine of x, which will graph just like y equals sine of x. And f of x equals cosine of x, right? So our base trig functions are those. And then we'll do function equals tangent, cotangent, secant, cosecant, and just a bit. All right? But let's look at the graphs of these. So once again, I'm on Desmos. I'm sure most of you have seen the graphs, but I'm going to graph them anyways. So f of x equals sine of x. Notice we have this pattern. We have a wave. At the very top points on this wave, it goes up to 1. At the very bottom points, it goes down to -1. All right. And you can kind of see the idea here. One way to think about it is think about going around the unit circle. As you go around the unit circle, your y value on the unit circle goes up to 1 and down to -1. And the height on the unit circle is what this is tracking. Does that make sense? So this is tracking the height on the unit circle. So the range of sine of x goes from -1 to 1. All right. Now, if u f of x equals cosine of x, we get the exact same type of wave where we're going up and down, oscillating between -1 and +1 for our y values, except obviously it's scooted over. So the red, which is sine wave, is going to track as you move around the unit circle, how far up and down you go. The blue, the cosine tracks how far left and right you go on the unit circle. That makes sense? But again, they're the exact same wave. So those are our base functions. Now, what we're going to do to those base functions is we're going to start putting values out front. Let's say we put the number 2 out front. Well, now, I should have probably, let me put number 1 out front for a second. I want you to notice where the sign is 1 and where it's -1. It's 1 at pi over 2, and 3 pi over 2 is -1, 5 pi over 2 is +1, right? Odd number times pi over 2 either gets you to positive or -1. Okay. It crosses the origin, and then every time it hits the axis, it's at pi, 2 pi, 3 pi, 4 pi. You can see all of those. But if we put a number out in front, so let's put the number 2. All of a sudden, the high point still stays at x value of pi over 2, but the y value goes up to 2. Does that make sense? And if we did a 5, same idea. That wave just gets bigger. By the way, if we throw a negative in front of this, it's just going to flip upside down, right? We should have known that, or we probably already knew that by looking at translations and shifts from what we've done previously. So putting a number out front is just a vertical stretch, right? Putting a number out front, just a vertical stretch. Okay. Putting a number inside, let's say we put the number 2 inside. Oh, that's a horizontal stretch or shrink. Shrink in this case because it's a 2. So now that x value, they gave me my top point, changes from pi over 2 to pi over 4, right? So we got a horizontal shrink, got half. And then obviously we could shift it over any way we wanted, right? Move it over 2 units to the right by subtracting 2. If I subtracted 1, I'd move over 1 unit to the right. If I subtracted 3, I move 3 units to the right. So that origin point got moved over to here. Okay. So we can stretch it horizontally, we can stretch it vertically, we can do, oops, oh, that was there. Yeah, that's right. Stretch vertically, stretch horizontally, we can move it left and right. If we ever wanted to move it up and down, as usual, we just add a number on the end. Okay. So add 3, add whatever. Now, those are just our normal translations and of our functions, right? Vertical shift, horizontal shift, vertical stretch or shrink, horizontal stretch or shrink. All right, but they're going to have some special names when we get into trig functions. So it's the same thing we've been doing, but they're going to have some special names. Before we talk about those special names, though, well, one of them is going to include this. I need to talk briefly about why these two functions and the other trig functions as well will be what we call periodic functions. All right. So what's a periodic function? A periodic function is a function, we'll call it f of x, such that f of x plus p is equal to f of x for all x for all x. I probably should have missed one. I should say such that there is a p such that you guys get that. There exists a p. There exists a value which has this property for all x and some value of p. So in other words, a periodic function is a function that has a repeat. And we saw on our graphs of our base functions, f of x equals sine x and f of x equals cosine x, that we have this sine, the wave. And you can cut a piece of that wave and just repeat it over and over and over again. Okay. P is called the period. F of x. And the smallest p is known as the fundamental period. By the way, we always assume P is positive here. And obviously, this would be true for every function if you let P be 0, right? But that's irrelevant. We're saying that there's some positive P that you can shift it. This work. So periodic function is one that repeats. Let's take a look at our examples, or our example in Desmos. So we have sine x. There that is. And let me do a shifted version of sine x. So let's do sine of x plus a, where a is a slider. Okay, that makes sense? So there's our sine x, okay? If I start sliding the a over, not yet, not yet. Notice that we're getting closer and closer and closer. And right now, I'm essentially right on top of my old curve, right? So as I shifted it over about 6.3 units, we were basically on top of my old curve. Now, 6.3 is not the exact shift. Anybody know what the exact shift is? Go for it.
Is it 2 pi?
2 pi, exactly. Yeah, 2 pi. So the slider only goes over by tenths of units. So, but that should be 2 pi. 2 pi, when we shift by 2 pi, we get back the original curve, right? Now let's take out cosine. You can guess what's going to happen here. Let's do that. Same slider. So again, start back at a equals 0. There we go. So when a is 0, cosine and cosine of x plus 0 are the same thing. And as we shift over, I'll shift this one a little bit faster. Sure enough, 2 pi again, right? So both of these functions have period of 2 pi. And that should make sense if we consider where we got these values from. These values came around the unit circle. So as we moved around the unit circle, excuse me, let me write that. They have period of 2 pi, but they have fundamental period of 2 pi. Alright, so I'm gonna write that down. They have a fundamental period of 2 pi. That means also 4 pi is also a period of these two functions. That makes sense? And 8 pi is also a period. So why would that be? And again, remember where sine and cosine came from. There was a point on the unit circle, centered at the origin. That was cosine theta, sine theta, where theta was the angle between the x-axis and the ray from origin to that point. And so, again, if I'm looking for cosine, it's the x value. Well, as I add 2 pi, I'm back to the same place I started at. I take this cosine of theta, I add 2 pi to it, I go all the way around the circle, and I'm back to that same point. Okay? So no matter where you're at on the circle, you add 2 pi to it, you get back to the same value of cosine, you get back to the same value of sine. So theta plus 2 pi is the same angle as theta. Is that right? So those are periodic. Now, before I move on, and again, this is why I want to do 6-1 and 6-2 together. I'll come back to sine and cosine in just a moment. But let's take a look at the graphs for tangent and the graphs for cotangent. I'll write these. By the way, since cosine and sine have a period of 2 pi, and tangent can be thought of sine over cosine, right? Tangent should have a period 2 pi, but it might not necessarily be the fundamental period. Does that make sense? So that's going to be one of the periods, but it's not necessarily the fundamental period. Same thing with secant and tangent. Secant is 1 over cosine, so it's going to have a period of 2 pi, but it might not be the fundamental period, so we'll have to check that out. Sine and cosecant work the same way. Sine has a period of 2 pi. Cosecant must have a period of 2 pi, but we'll check to see if it's the fundamental period or not. So let's look at some of these graphs. All right. I think what I want to do, yeah, cancel my cosines down. All right. Let's go. y equals tangent of x. If I do y equals tangent of x, notice that, again, we go through the origin, but what happens is we get, well, essentially a lot of asymptotes, right? If you look at where these asymptotes are, they're at pi over 2. And over here, that would be 3 pi over 2. See that? And over here, it would be 5 pi over 2. And so on and so forth. And negative pi over 2 as well. And negative 3 pi over 2 as well. So we get lots and lots of asymptotes with tangent. And as you can see, while sine and cosine had maximum and minimum y values of 1 and negative 1, tangent goes off to infinity. And goes down to negative infinity. All right. Now let's take a look at, I'll zoom in a little bit. Determining the phase shift. Now, notice this is x plus 2 pi, and it landed right on top of tangent. So that's what I was saying earlier. If sine and cosine both have period 2 pi, then tangent's got to have period 2 pi as well. But interestingly enough, let's go back down to 0. So that's just tangent by itself. If I shift it over 1 unit, 2 units, 3 units, 3.1, almost there, right? So notice that tangent, yes, it has period of 2 pi, but the fundamental period is pi. We're okay with that? Fundamental period is pi. Go back down to 0. If that works that way for tangent, you should probably say, oh yeah, cotangent does the same thing. Notice, by the way, the difference between tangent and cotangent. One, as you move from left to right, you're going up. But see that? That's the tangent. So this is tangent. As you move left to right, you go up. Does that make sense? And then cotangent, as you move left to right, you go down. Also, the asymptotes are in different spots. Tangent, the asymptotes were at pi over 2, 3 pi over 2. All the places where sine would be 0. Or sine would be. Wait a second. No, not sine would be 0. All the place where cosine would be 0. That's your asymptotes for tangent. For cotangent, it's all the places where sine would be 0. 0, pi, 2 pi, etc. That makes sense? Cotangent, as you move A over, oh shoot. As you slide things over, once again, sure enough, fundamental period of cotangent is pi. I'm going to write all this stuff on the board in just a moment, but I wanted to play around with Desmos before then. Let's do secant. Well, secant looks like this. Looks like a bunch of U's and upside down U's. Let me draw one thing. X equals, I keep mentioning. Asymptotes. Notice that pi over 2 is the asymptote for secant. And that's when your cosecant is 0, right? Because it's 1 over, did I say cosecant? That's when your cosine is 0. Same thing, 3 pi over 2 is where cosine is 0, and therefore secant has an asymptote. 5 pi over 2, we have an asymptote. Notice that your secant never crosses the x-axis. Yeah. Secant never crosses the x-axis. All these U's and upside down U's. Same thing is going to go for cosecant. Looks exactly the same as secant, except moved over a little bit. So we have different asymptotes, and our asymptotes line up with where sine would be 0. So like 1 pi, 2 pi, 3 pi, -1 pi, 0 pi, all those types of things. Let's figure out the period of cosecant. So there's cosecant, and a cosecant with a shift of A. If A is 0, if there's no shift, they're the exact same things. As you move over, if I move over pi units, no, it doesn't get on top, does it? But if you move over 2 pi units, we are on top. And it probably suffices just to say that secant has the same property. So the period of secant is 2 pi. The period of cosecant is 2 pi. All right. So just so that we're on the same page, let's do some graphs. Right? So it looks something like that. And the period of tangent, I should say the fundamental period of tangent is pi. Cotangent with something like that. It's kind of like tangent, but upside down and with a shift. Right? And the fundamental period there is also pi. for secant and cosecant, we get those U's and upside down U's. And it turns out that not very good at drawing these where they should be, but hopefully you get the picture. By the way, the furthest these go down is 1. And the furthest these go up is -1. All right? Same as cosine goes up. You know, the maximum range of cosine, well, let me rephrase that. The range of cosine goes from -1 to 1. If you take the reciprocal of anything between -1 and 1, you get essentially from -1 down to -infinity, from +1 up to +infinity. The reciprocal of a number that's less than 1 becomes greater than an absolute value. And again, fundamental period. Is 2 pi there. Same thing over here, except to shift it over. Fundamental period. So those are our base trig functions. Okay, our base trig functions, we have 6 of them. The sine, the cosine, we'd already written out. And then these 4, they're connected to sine and cosine in a lot of different ways. Okay. Everybody okay with periods of functions? Periods of functions. Good. So those are our base ones. Now what we're going to do is we're going to translate and shift and, well, translate in general, shift and stretch, like I had mentioned before. Okay. So let's talk about translations or transformations. Let's say we have y equals a times sine of bx plus c. I won't do a vertical shift yet, right now. We can always do a vertical shift by adding k on the outside or whatever it happens to be. And we'll also take a look at cosine at the same time because they are so similar. Sometimes these two functions are called functions of harmonic motion. Harmonic meaning we're having these traveling in waves. Does that make sense? So if you ever hear harmonic motion, that's what we're talking about. Now, we kind of saw earlier on decimals that if I put a number in front, we know that vertically stretches or vertically shrinks depending on what the number is. And if the number is positive, it stretches or shrinks. If it's negative, it also flips the whole thing, right? We actually have a name for that in harmonic motion, right? So these are graphs of harmonic motion. A, and I'll use the absolute value of A, so we're talking about that, is known as the amplitude. So if you think about a wave, far up and down, right? So A is called the amplitude of the wave, so we call that the amplitude. Now, if we ignore the C for just a moment, C is just going to be a horizontal shift left to right. There's a special name for that in harmonic motion functions, but get to that. What this B does is it's a horizontal stretch or shrink, okay? And as B gets bigger, the waves get smaller and smaller and smaller, more compact. Does that make sense? And if originally sine, well, let me explain this to you real easy way. Let's say we have a sine of 3x. You don't have to write this down. Let's just talk through it. If I was able, in my original function, y equals sine of x, when x equals 0 and x equals 2 pi, these things have the same outcome, right? Because we have a period of 2 pi. Well, now, notice that when x is equal to 0, if I have a 3 in front of that, then x equals 2 pi over 3. Those are going to have the same outcome, same output. Does that make sense? So by multiplying by 3 here, it shrinks the wave period by a factor of 3. Cuts it in third. Does that make sense? Okay. And so all I'm saying here is that now that we have B in front of the X, the period or the fundamental period is now 2 pi divided by B. Or sometimes people would say absolute value of B if B happened to be negative. We don't have negative B's. Hopefully that makes sense. So if you multiply inside by B, it shrinks. So if you multiply by 3, shrinks that wave down by a third. Because now you can complete the wave by the time you get to 2 pi over 3. And the x value. And then we know we shift left and right because we've seen that before. With harmonic motion, we call this a phase shift. So we have a phase shift. And this is kind of where we deviate a little bit from what we've done before. A lot of times what we've done before is we put a minus in here. And it was like minus x minus h. And we say, oh, we shift horizontally by h with doing x minus h. Now we say, well, let's shift by negative c over b by putting a positive c in here. Again, why they do that, I don't know, but it's just the way it is. So those are graphs of, well, excuse me, this is how sine and cosine work with all their translations. And because sine and cosines are harmonic motion, we have these new terms like amplitude, period, phase shift, rather than vertical stretch, horizontal stretch, horizontal translation. Does that make sense? That's the idea. All right, so let's do a couple of problems. Oh, shoot. Yeah, I can do that. Let's find the amplitude, period, and phase shift. For f of x equals 5 cosine of 4x minus 1. So we have amplitude these are pretty straightforward, hopefully, from what we just did, is 5. By the way, if you put a negative in front of that, not a big deal. The period, by the way, whenever it asks you for the period, we're generally speaking, we're just going to use the fundamental period. All right. So it says find the period, usually talking about the fundamental period. Okay. Fundamental period is going to be 2 pi divided by 4. And in Moodle, I think it's going to ask you to round that to 2 decimal places. So about 1.57, that's pi over 2, but about 1.57. And then the phase shift is going to be, well, negative of -1/4. Which is a positive 1/4. Okay? Good. All right. Let me do another version of that. On Desmos, here we have a graph. Now, I'm not going to phase shift this at all, so there's no phase shift in this. This graph, as you can see, goes to the point 0, 0, and it's this nice harmonic function. So it's going to deal with sine. It's going to look like y equals a times sine of bx. Right? So there's no phase shift, the c is 0. And it's going to be a sine function. So if I said, oh, you guys understand how I know that's a sine function? It goes through the origin, right? Cosine does not, unless it has a phase shift, but it doesn't. And also, if I said, what's the A? Is it positive or negative? Notice how as you go through the origin, you go from left to right, your point moves up. That means the A is going to be positive. If it went the other way, the A would be negative, left to right going down through the origin. All right, so if you're looking at the amplitude, all you're looking for is these top values. And obviously, the bottom values. But I'm going to give you, it's not going to have any vertical shift in it. So notice the top values at all the points are 6, the bottom values are -6. So that means the amplitude is 6. And moreover, the A has to be a positive 6 because left to right, we're moving up through the origin. So amplitude there is 6. Now, here's the other thing. What's the period? There's a couple of ways to see this. All right. One way to see this is ask yourself, normally we go through one full up-down rotation in 2 pi units. So usually we go up, down, into 2 pi, we hit back 0, we get 1 rotation. That makes sense what I mean with 1 rotation. Rotation, I'm referring to around the unit circle. So we start at 0, 0, we go up, we go down, we go back up, and right here, we hit 2 pi over 3. That's a full rotation, and I'm back moving in the exact same way I was when I started at the origin. See that? Now on Desmos, that's really easy to see because you can click on the point and say, oh yeah, that's a little bit over 2. And they click on the point and it says exactly 2 pi over 3. So it's pretty easy that the b in that equation would have been 3, and that your period now is 2 pi over 3. So that's one way to do it. Another way to do it is to say, well, between 0 and 2 pi, I typically get 1 rotation. How many rotations through my wave do I get when I get to 2 pi? And you can see, well, you get 1, 2, 3 rotations through your wave, right? 3 waves from 0 to 2 pi. So I know exactly what that equation is going to look like. That equation that I just had would be f of x equals 6 sine of 3x. Right? With amplitude 6, period of 2 pi over 3. Everybody see that? If your number out front happened to be a number that's less than 1, then you ask yourself, well, how many times do I get, how long does it take me to get through 1 full wave, right? Or 1 full rotation around the circle. So 1 full wave, 1 full rotation around the circle. And if this were like 1/2, then it'd take you twice as long. It wouldn't take you 2 pi, it'd take you 4 pi to get through 1 whole wave. Is that all right? Now let's do one or the other. Oh shoot, I wanted to mention something. On sine and cosine, the reason this is called the amplitude is because related to waves, right? It's how far up, how far down that wave goes. Okay. When we deal with things like tangent and secant and cosecant and cotangent, we no longer call that an amplitude, right? So if I gave you a question and I said 2 times the tangent of 5x plus 2, and I say find the amplitude, period, phase shift, you'd say, well, actually the amplitude, since tangent goes off to infinity, down to negative infinity, we really don't talk about tangent anymore. Or say that, we really don't talk about amplitude in relation to tangent anymore. So there's no amplitude here. So there's no amplitude, or the amplitude is infinite. There is a vertical stretch of 2. Does that make sense? The period on tangent used to be pi. with our base function of tangent as period of pi. Now that we have a 5 in front, instead of taking pi for the exact same reasons we did earlier, period is going to be pi over 5. Right? And the phase shift exactly the same thing as this one. -2 over 5. Does that make sense why the period's pi over 5 now instead of 2 pi over 5? 2 pi was the period of the base function of sine and cosine. It's also the period of secant and cosecant. And so those all have periods of 2 pi over b when I put a b in front of x. Is that right? Nothing too crazy. So,
Jordan?
oh, yeah.
Really quick, would you re-explain to me why is the amplitude, why does it not exist for that question?
Okay, so amplitude is talking about how a wave, all right? So if you think about the amplitude, that's why this is graphs of harmonic motion. We're talking about waves here, sine and cosine. And in the context of a wave, it's like how far up and how far down it can reach compared to the base level. That's why we're not doing a vertical shift, because we're always comparing it to the base level. So amplitude is how far up this wave can go, how far down this wave can go. Because tangent goes all the way up to infinity and all the way down to negative infinity, even though there's a vertical stretch when I multiply by 2, the amplitude doesn't exist because there's no maximum value at which tangent can go. Is that right? So amplitude's kind of referring to the maximum value of your wave. Where here, while we do have periods, the actual value shoots off to infinity. You can think of the amplitude as infinity in some cases if you want, but usually we don't.
Gotcha. Thank you.
Yep. So that's why amplitude doesn't exist, even though there's a vertical stretch. All right. Good. All right, so we talked about some transformations. I'm not going to deal with a whole lot of transformations. You can kind of see what pretty straightforward here. Just be careful that the period is our original period divided by whatever this b is, whatever this coefficient of x is. And sine, cosine, secant, cosecant, the original period is 2 pi. Whereas tangent, cotangent, the original period is top. Right? Oh, we haven't done one. Maybe I should do one of these. Let's do one more, I guess. Amplitude, period, all that stuff. If I have 7 times secant of x over 3. We haven't done one with secant. We haven't done one with a division yet either. Okay, again, since it goes off to infinity, amplitude does not exist. Even though there is a vertical stretch of 7. All right. Oh, and on Moodle and stuff, I wanted to check this amplitude. When the amplitude doesn't exist, just write D and E in capital letters. Okay. So it says that on the problem, but that's fine. All right. When you go to calculate this period, this fundamental period, notice that we're dividing by 3. So that's like taking my original period secant, which is 2 pi, and dividing by a third, which is the same thing as multiplying by 3, right? So dividing by a third is the same thing as multiplying by 3. And so you get a period, fundamental period, in this case, of 6 pi. Phase shift here is 0, obviously. We don't have a plus C. We don't care if amplitude, period, phase shift stuff. Once they go off to infinity, amplitude doesn't exist, even though there is a vertical stretch on. So only sine and cosine have amplitudes. Now, the other part of these graphs that we want to focus on is where the x-intercepts or the zeros are. So we're going to find the zeros of trig functions. So remember talking about x-intercepts when we talk about zeros. So let's start with our base function. F of x equals sine of x. F of x equals cosine of x. Think about going around the unit circle, or think about the graph. It doesn't matter how you do this, how you think about it. As you go around the unit circle, when do the y values on the unit circle hit 0? Well, at 1. When the y value is 0 here and here. Right? So as you travel around the unit circle, you have a 0 when x is pi, when x is 1 pi, when x is 2 pi, when x is 3 pi, when x is 4 pi. And you could have also said when x is 0, when x is negative pi, when x is negative 2 pi, and so on and so forth. Okay. So the zeros of our base function when x is, you'd have done that forever. I'm just gonna write negative 2 pi, negative pi, 0, positive pi, positive 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 28 pi, all that stuff. So the zeros for sine of x are just when we have an integer times pi. It's k times pi whenever k is an integer. How about for cosine? Well, you can think about unit circles again. When is the x value on a unit circle 0? By the way, I hope this isn't super confusing. We're kind of going back and forth between two different types of when I say x values, okay? X values on a unit circle, I'm talking about cosine of an input of theta. When I'm talking about a unit circle x value, I'm talking about cosine of that. But when we translate that into functions, my variable usually is x in a function instead of theta. So when the input of cosine, when is the input you plug in of cosine give you a value of 0? Well, on the unit circle, when the unit circle's x value is 0, right? Not when this x value is 0, but when the unit circle's x value is 0. It's very, sometimes that's hard to keep track of. We've got a lot of things going on. But when are the inputs giving us 0? Well, when the angle is pi over 2, when the angle is 3 pi over 2, when the angle is 5 pi over 2, when the angle is 7 pi over 2, and we could have also went negative pi over 2, negative 3 pi over 2, negative 5 pi over 2, negative 7 pi over 2, et cetera, et cetera. So when the zeros happen when the inputs are negative 3 pi over 2, negative pi over 2, positive pi over 2, a positive 3 pi over 2. You know, then you can keep going as far as you want. 5 pi over 2, 7 pi over 2. What's the pattern? Well, it's always odd integer times pi divided by 2. you know, one way to write that. What's an odd integer times pi over 2, except a pi over 2 shift from these numbers? If you add pi over 2 to 0, you get pi over 2. If you add pi over 2 to pi, you get 3 pi over 2. If you add pi over 2 to 2 pi, you get 5 pi over 2. That makes sense? So if you just add pi over 2 every time to these, so sometimes people write k is equal, or excuse me, x is equal to pi over 2 plus k pi, where k is an integer. That should make sense, because every time we have a sign value that gives us 0, if I rotate by pi over 2, now I have a cosine value that gives me 0. So every time I had a sine value that gave me 0, rotate pi over 2, now I got a cosine value that gives me 0. So those are the inputs that give me zeros for my sine and cosine. Okay? And hopefully we all know zeros and x-intercepts are the same thing. Zeros are the x values of the x-intercepts. So when it says what are the x-intercepts, those have those x values. All right? So sine and cosine have those zeros. Now we can do, there's going to be 2 different directions we go from here. All right? 2 different directions. Let me first off go to the direction of, let's talk about other trig functions. Okay. Let's talk, for instance, about tangent now that we know these 2. Now that we know these 2, let's talk about both the zeros and the asymptotes of f of x equals tangent of x. So we're going to find both the zeros and the asymptotes of tangent. And we're going to do this algebraically. All we have to do is remember that tangent of an input is the same thing as sine of that input over cosine of that input. Tangent is sine over cosine. So if we're looking for the zeros of tangent, those happen when sine over cosine is equal to 0. And you'll notice the denominator is never going to affect this. You just multiply both sides by cosine. So the zeros of tangent happen when sine is 0. We already know when sine is 0. So all we have to do is say the zeros are x is equal to negative, well, I kind of like writing out negative 2 pi, negative pi, 0, pi, 2 pi, 3 pi, instead of writing integer times pi. Integer times pi is the more efficient way to write it, but I like writing out the zeros. And one of the reasons I like writing out the zeros is oftentimes we will look at our tangent in a range of numbers. So if it said find the zeros between negative 2 pi and positive 2 pi, then all we're talking about is the zeros between here and here. Does that make sense? Is that okay? And similarly, if I'm talking about where the asymptotes are, the asymptotes happen when tangent does not exist. Or when the denominator is 0. And we say, well, obviously, it's when denominator is 0, that's when cosine is 0. So the asymptotes for tangent happen at these values. They happen when x is negative 3 pi over 2, negative pi over 2, positive pi over 2, 3 pi over 2, 5 pi over 2, et cetera, et cetera. And again, the reason I like writing them this way is because sometimes the book will ask you where are all the asymptotes between negative pi and 3 pi. And then you say, well, negative pi, that's between here and here. And then 3 pi is like right here. So it's these 4. And just list out those 4. Or if it said, where are all the asymptotes between 0 and 2 pi? Well, 0 is between here and here. 2 pi is right there. So all the asymptotes between 0 and 2 pi are just those 2, right? So those are how you get the zeros of other trig functions. and asymptotes of other trig functions. In a similar way, you can do cotangent, and the numerator of cotangent, well, cotangent is cosine over sine, so it works in the reverse way, right? Where you get the asymptotes and zeros. If I said find the zeros and asymptotes of cosecant of x, cosecant is 1 over sine. And so if you're looking for the zeros, they happen when that fraction is equal to 0, but notice the numerator can never be 0, right? So this is an algebraic way to see that cosecant never crosses the x-axis. We actually saw that graphically earlier. You remember that? We looked at the graph and saw secant and cosecant never cross the x-axis. So there's no zeros here. So we've never crossed the x-axis. Asymptotes are a different thing. Asymptotes in the cosecant happen when that fraction 1 over sine of x doesn't exist. And so we're saying asymptotes happen when the sine is 0. And we know when that is 0. We add that bit down. Earlier. Negative 2 pi, negative pi, 0, pi, 2 pi, et cetera, et cetera. So those are the zeros and asymptotes discussion. Now, like I said, we could go through one of two options, and they're kind of two paths going down the same direction. So I started by looking at zeros of sine and cosine. That allowed me to look at the zeros and the asymptotes of my other trig functions. Okay. My other base trig functions. And now what we're going to do is we're going to say, well, what about the zeros and asymptotes, not of the base trig functions, but what are the zeros and asymptotes going to be if I have a translated trig function. So let's take a look at this. Let's say f of x is equal to 3 times the sine of 4x. We'll find the zeros and asymptotes, but in this case, there's no asymptotes, right? It's just a sine function. So might as well just find the zeros. So the zeros happen. When my output is 0, also graphically, when we cross the x-axis. What I would do is I would simply solve this. Divide by 3. And we get sine of 4x is equal to 0. Now, I just want you to remember we just got through saying that if you have sine of something equal to 0, then that something could have been negative 2 pi, negative pi, 0, pi, 2 pi, 3 pi, whatever, right? So we just got done saying that. Well, that's the truth where if we're talking about theta in there, or earlier we just had the letter x in there, or now we have 4 pi in there. So all we have to do is say, well, this is true. I know when sine is 0, then my argument on the inside of the sine has to be something like negative 2 pi, negative pi, 0, positive pi, positive 2 pi, positive 3 pi, etc. So we get infinitely many options for what 4x could be. And if we wanted to solve for x, what would we do? Well, we just divide all of my answers by 4. Like for instance, if I said 4x is equal to pi, what would you say x is? Pi over 4, right? If I said 4x is equal to 2 pi, how could I solve for x? It'd be 2 pi over 4. Does that make sense? So I just have to multiply everything by 1/4 or divide everything by 4. I'll divide everything by 4. So my zeros happen when I get negative 2 pi over 4. You could reduce that, but I don't want to at this stage just because I want to see the pattern in my notes. Does that make sense? Negative pi over 4. 0 over 4, which is 0. I guess I can do that one. Pi over 4. et cetera, et cetera, et cetera. Okay. And you can keep going with that pattern as far as you want. 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4. As far out as I want. So that's the other direction we could have gone in. That I did. So I went to other trig functions first, and then I went to different arguments. Second. I could have gone to different arguments first, and then went to other trig functions from there. Either way. That work? All right. I want you to try this on your own. Let's do zeros and asymptotes. Of f of x equals 7 times tangent of 2x. So combine other trig function stuff we just worked on with the horizontal shift and the horizontal stretch, shrink. Now, I know I didn't explicitly state this before, but I probably should have forewarned you that all of my answers here, we've been writing in radians, okay? So I know when we dealt with right triangles, we went back to degrees. And then I didn't state this explicitly, but when we're dealing with functions, usually we're dealing with radians, okay? Because that's the connection to the inner circle. That's the connection when we're dealing with calculus topics. We're typically talking about the function, f of x equals tangent of x or sine of x or cosine of x. We're talking about that in context of radians, all right? So if you didn't catch that, you probably caught it anyways, but if you didn't catch that, I apologize, I should have said that. But dealing back with radians again. All right, so when we find the zeros and asymptotes, we're looking for radian angle measurements. That's all I'm saying. That's all I'm trying to get at. All right, zeros and asymptotes of 7 tangent of 2x. So we set 7 tangent of 2x equal to 0. We can divide both sides by 7. And then I rethink tangent as sine over cosine. And I say that fraction is 0 when sine of 2x is 0. When the numerator is 0. And I know that if sine of something is equal to 0, then that something has to be like negative 2 pi, negative pi, 0, positive pi, positive 2 pi, 3 pi, et cetera, et cetera. And then I simply say, well, going from 2x equals all of these to x equals something, I just have to divide everything by 2. And you can imagine if your argument was more complicated, like let's say 2x plus 5, you have to then subtract 5 and then divide by 2. Right? So we get the zeros that are negative 2 pi over 2, negative pi over 2, 0 over 2, positive pi over 2, 2 pi over 2, 3 pi over 2, et cetera, et cetera, et cetera. To get that pattern. Okay. And if you wanted to simplify these, negative 2 pi over 2 is just negative pi. 2 pi over 2, that's positive pi. You know, so if you want to simplify, you could. I'm not going to right now. I don't think it's needed, but if you wanted to, you can. Very similar on the asymptotes. On the asymptotes, we say, where does this thing not exist? 7 times 10 and 2x. The 7 up front is not going to matter. Divide by 7, it still doesn't exist. multiplying by 7 still doesn't exist, right? So you have something that doesn't exist and you multiply it by 7, it still doesn't exist. That's all I'm trying to get at. You have something that doesn't exist, you divide it by 7, it still doesn't exist. So asymptotes happen when this does not exist. So in the denominator, is 0. And we just saw where cosine was 0. Cosine is 0 with the argument inside. Negative 3 pi is negative 3 pi over 2, or negative pi over 2, or positive pi over 2, or positive 3 pi over 2, or positive 5 pi over 2, or positive 7 pi over 2. And then divide everything by 2. What's going to happen? All those denominators are going to go from 2 to 4. Right? Does that work? So these are where the asymptotes are. One other way you could phrase that, instead of saying where's the asymptotes, you could also say where is the function undefined. So asymptotes are here. Are at these values. And the function is undefined at these values too. So function is undefined or the asymptotes are here. Both are the same meaning, okay? So both are the same meaning, just like the zeros are here or the x-intercepts are here. It's the same meaning. So if it asks you to find the x-intercept values, you're looking for these. If you're looking for the zeros, you're looking for these. If you're looking for where the function is undefined, or where the function has asymptotes, you're looking for the same thing. Okay. All right. Any questions about zeros of trig functions or asymptotes of trig functions? It all kind of stems from that when it's sine 0, when it's cosine 0. And if you know those two things, then everything kind of flows from there. And your basic identities of functions, like tangent is sine over cosine, cotangent is cosine over sine, secant is 1 over cosine, and cosecant is 1 over sine. Those identities are there. Now the last bit in 6.1 and 6.2 that we're gonna cover is the idea of even and odd functions. In relation to the trig functions. Now, I think the last time we talked about even and odd functions was section 1.5. So it's been a minute, okay? Let me remind you what even function meant and what an odd function meant. An even function has the property that if you plug in a negative x into your function, you will get the same output as if you plugged in a positive x in your function for all x. If you think about this graphically, that means it is symmetric about the y-axis. An even function is symmetric about the y-axis. Even. An odd function has the property that if you plug in a negative value for x, a negative x, your output is actually the opposite of what you get when you plug in a positive value for x. For all x. And again, back in 1.5, we saw what even and odd functions we did. We saw even functions meant symmetric about the y-axis, and odd functions, if you remember, mean we're symmetric about the origin. So odd functions are symmetric about the origin. Now, I very quickly mentioned something about when we do the unit circle and we have an angle theta, And then if we had a negative theta, notice that we get cosine of negative theta, sine negative theta. What happens with cosines? Those are the same x values, aren't they? Those are the same things. What about sines? Well, those are the y value and the opposite y value. So what we're saying, unit circle wise, is that if you input a negative angle into cosine, you get the same as you got when you input a positive angle. Exactly what this is, right? And sine, you get the opposite of the output when you input the negative angle as when you input the positive angle. Now you can see that on Desmos as well. So if, oops, thought I had that up there. You go to Desmos, and you look at sine. Well, sine is symmetric about the origin. Every time I have a point over here, like 2.57, positive 0.541, if I go over here to negative 2.57, I get a negative 0.541. See that? Symmetric about the origin. If I draw a line through the origin, they match up. Okay. Cosine, oops, is just the reverse. Cosine, oops, I'm sorry, you can't probably see that here. Cosine, you can see it pretty easily. We have some symmetry about the y-axis. If I plug in, I don't know, 0.9, I get a 0.622. I plug in negative 0.9. I still get 0.622, hopefully. Yeah, there you go. So whether you look at the graph of cosine and then the graph of sine, you can see the graph of sine is symmetric about the origin. The graph of cosine is symmetric about the y-axis. So sine, therefore, is odd. Cosine is even. And I hope you remember that not every function is even or odd, right? There were a lot of functions that were neither even nor odd. And that's just the way it goes. Using these two properties, the fact that cosine is even and the fact that sine is odd, you can figure out, for instance, whether cotangent is even or odd. Or some weird combinations of things are even or odd. Let me give you an example, or give you a few examples. So let's determine whether a function is even, odd, or neither. Let's start with the function cotangent of x. So what I would do is I would input a negative x value. If I can rewrite this such that it is the same as f of x, then I know it's even. If I rewrite this so that it's the same as negative f of x, then I know it's odd. We get that? And if I can't do either of those two, I know that it's neither. Okay? So the trick, the algebraic trick, again, this is the same thing we've been doing that we did back in section 1.5, the algebraic trick. We plug in a negative and we just rewrite. Plugging in the negative into cotangent is like taking cosine of negative x divided by sine of negative x. Cosine of a negative is the same as cosine of the positive. So that is the same as cosine of positive x on top. Sine of a negative x is the same as negative sine of positive x. And I can factor this negative from the denominator into out front. So just based on those two things, that is negative of the cotangent of x. Notice that's the opposite of my f of x, right? That's the opposite of what I started with. So in this case, when I plugged in a negative, I got out the opposite of the output when I plugged in a positive. What's that mean? That means cotangent is odd. Right, that is by definition what odd means. When you plug in a negative, the output gives you the opposite of the output when you plug in a positive. And so cotangent is odd. Any questions about that? It's pretty easy. Pace through it. Let's do another one. I'll do g of x this time, so it's not as easy. Let's take g of x equals x squared times the cosecant of x. Everybody get what I'm doing there? X squared times the cosecant. So, as always, to see whether something's even, odd, or neither, I plug in a negative value. Now, be careful here. We have two values, two places where x is at. One is in the square, so we're going to have to plug in negative x and then square it. And the other is in the cosecant. I'm going to rewrite that because cosecant, let me say cosecant. Cosecant is 1 over sine, right? So I'm just going to put this as sine of negative x in the denominator. I'm going to change cosecant to 1 over sine. Is that all right with everybody? Cosecant is 1 over sine. So cosecant of negative x is 1 over sine of negative x. Now, in the top, negative x squared, if I take negative times negative, I get a positive. X times x is x squared. So in the top, I got x squared. In the bottom, well, once again, signs in the bottom, I can do the same trick I did before. Sine of negative x is negative sine of positive x. I'm going to rewrite this. X squared, I have a negative sign, so I can go to negative x squared, and I'm going to rewrite the sign in the denominator as cosecant of x. Notice that's negative of what I started with. So that means this function, x squared times cosecant of x, is also odd. Alright. We got two odd functions in a row. Now, not everything obviously is gonna be odd function. And cosecant, by the way, is not odd, it's even. Other functions are not odd. Other functions are not odd, they're not even either. Let me give you at least one example of something that's not odd. So let's determine even odd or neither on this function. I'll go back to using f. F of x equals cosine of x plus x to the third. So to test whether this is even, odd, or neither, I'm gonna plug in a negative x. I have to plug in the negative x into everywhere I have an x. Now, cosine of negative x, since cosine is an even function, cosine of negative x is the same thing as cosine of positive x, right? So this part is even, and I get cosine of negative x is the same as cosine of positive x. However, we all know what happens with x to the third. When I take a negative x to the third, negative to the third is still negative. And so I basically get minus x to the third. Now you'll notice that this is not the same thing as our original function. This is not our original function. That would have been even if this was our original function. And it's also not the negative of my original function, because if I had a negative of my original function, both pieces would have to be negative, right? Both terms. So it's also not negative f of x. So my function, so my function is neither even nor odd. Is that okay? So you can determine whether a function is even or odd just by plugging in a negative x into the function and then doing some algebraic things and seeing, do you get the same as your output? If you do, good. If you get the same as your negative of your output, you got the same as your output, you're even, negative of your output, you're odd. Okay. Notice, by the way, some of these, this is an even function times an odd function. When I had even times odd, I got odd. Even and odd kind of work like negatives. If I multiply two negatives together, I get a positive number. If I multiply two odd functions together, I get an even function. If I take even times an odd, that's one negative, that's like an odd. Does that make sense? So when you multiply even and odd kind of works like a negative number, and even works kind of like a positive number. By the way, when you add a negative number plus a positive number, you might get negative, you might get positive, you might get nothing, right? You might get 0. That's what we did here. We added an even function plus an odd function, and we got neither. All right. All right. We're done with 6.1 and 6.2. That's basically all it is. There's a couple of theoretical questions at the very, very end, but you can figure those out on your own. So you should be able to do all 6.1, 6.2 homework right now. And then other than that, we'll start on 6.3 next time. Okay? All right. See you later.